Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on XRF. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Greg Strassman, Scientific Fellow at EAG Laboratories.
Thank you, Rena. I'd like to welcome everyone to the next installment of our Smart Chart webinar series from EAG Laboratories. This week, we'll be talking about X-ray Fluorescence Spectroscopy, or XRF for short. A quick introduction. My name is Greg Strassman, and I've been a scientist at EAG for over 25 years, specializing in materials characterization. My focus for the last 15 years or so has been within X-ray based techniques, specifically XRF and XPS. As previously noted, the topic today is XRF. I hope you all had the opportunity to tune into our XPS seminar a few weeks back and the XRD, XRR, and AFM OP that followed. I'll begin the webinar with an introduction to EAG, then follow with a detailed description of our spectroscopy and microscopy analysis resolution tool, which is a bit of a mouthful, so we'll stick with the acronym and refer to it as our Smart Chart. After the introductory slides, the webinar will follow the format shown here, including fundamentals and some sample applications to explore the tremendous versatility of this technique. First, a brief introduction to EAG. EAG has several hundred highly educated scientists and engineers working in laboratories around the world. Our range of equipment and diversity of expertise allows us to offer comprehensive materials analysis serving many industries. We provide peer-reviewed reports, often within a few days of sample receipt, and when necessary, we can provide same-day service when a quick resolution is critical. We offer XRF in 2 locations, here in California and in our recent addition in the Netherlands. As mentioned, EAG services a broad swath of industries across the globe, from pharmaceuticals to aerospace, medical devices, to semiconductor manufacturers located right here in our backyard. I should also note that we do have an organization-wide quality system, either ISO 17025 or 9001 for many techniques, and we're both ITAR registered and DEA certified. We test instrument performance weekly and have external audits by both accreditation bodies and clients. We always like to start our technical portion of our seminars by introducing our Smart Chart. For years, this was simply called a bubble chart and has always been a must-have at our booths at technical trade shows. The Smart Chart encapsulates the broad technical capabilities of EAG in a graphical representation where their strengths and limitations can be easily compared. Along the bottom are imaging techniques that provide dimensional analysis or other surface properties. Detection limits, the y-axis on the chart, don't apply here. On the right are so-called bulk analysis techniques where samples are consumed in the measurement. Here it is the spot size that is not relevant. Inside the box are the techniques that generally operate as top-down sampling techniques at target surfaces. For these techniques, both analytical spot size and detection limits are relevant to determine which is most appropriate for any given analysis. Finally, you'll notice that the bubbles are color-coded. Blue indicates a technique that does strictly elemental analysis, while orange means that the technique can provide molecular or chemical state information, often along with quantitative or semi-quantitative elemental analysis. In this seminar, we're going to be discussing XRF, which is an elemental analysis technique, a blue bubble, that operates over large to moderately small sample areas. The technique measures elemental composition as well as trace level impurities in bulk materials, and also can measure thickness and composition of thin films. One last general information slide before we get into the topic at hand. This figure shows the approximate depth of analysis of various techniques at sample surfaces, and it demonstrates an important factor to consider when discussing these top-down analysis techniques, of which XRF is one. Even among techniques that probe elemental composition quantitatively, we always need to be careful when comparing data from techniques used to analyze the same sample, because the results may be very different depending on the total information depth being sampled. SEM-EDS is a technique that is often compared to or used interchangeably with XRF. In fact, both techniques are measuring the same signal, fluorescent X-rays. However, EDS is significantly more surface sensitive than XRF, so near surface composition will be more heavily weighted in the results. Techniques like XPS and Auger are even more surface sensitive, with the entire signal generated from approximately the top 100 angstroms or less. I want to stress that this is not a disadvantage or a weakness. It just means we need to tailor our choice of tools to fit what we're trying to measure. And often these techniques with their different sets of data will help paint a more complete picture of the material we're analyzing. So let's get started with today's topic, X-ray fluorescence. XRF is a very versatile technique that can provide compositional analysis on a wide variety of materials. In our lab, it is often considered one of the kitchen sink techniques that we can almost always turn to for obtaining at least some relevant information in a characterization project. The technique can provide quantitative compositional analysis in a survey mode for the identification of completely unknown materials, which may include residues, powders, or debris such as metal flakes that turn up where they shouldn't be. It's also used for verification of compositions of known materials, either to determine if they meet specifications or maybe to determine if the right glass or alloy was chosen for a specific application. XRF can measure both thickness and composition of thin films, even multi-layer films, and can do so non-destructively. The technique has a very wide dynamic range and can measure both trace elements in a matrix and the matrix composition itself in the same measurement. And with the appropriate instruments, we can analyze large samples, including wafers up to 300 millimeters in diameter. At our Sunnyvale facility, we have two Rigaku wavelength dispersive XRF instruments. The two instruments have very unique features that can make them well-rounded tools for many different applications. On the left, we have a Primus 2 instrument with a tube above design. That's the X-ray tube coming down from the top to sample the surface, or the sample. This instrument can handle samples up to 2 inches in diameter and about 1.5 inches in height. The sample tray holds 48 sample cups, and they can be run fully automated. On the right is our ZSX 400 instrument, which can accommodate large samples of different shapes and sizes, including 300 millimeter wafers, while also keeping the ability to use the smaller sample cups. Both instruments can analyze samples with 30 millimeter, 20 millimeter, 10, 1, and 0.5 millimeter diameter spot sizes, and are fully equipped with all the crystals necessary for boron to uranium analysis. So what is X-ray fluorescence? This diagram, which demonstrates the fluorescence process, is one you may have seen before if you tuned into our XPS seminar. While in XPS, the primary radiation is a low energy X-ray, such as the aluminum K alpha line at just under 1500 eV, the principal interaction of X-rays with matter still applies. With XRF, the sample is bombarded with a high energy X-ray. Rhodium is probably one of the most common sources used, but there are many other choices as well. This bombardment liberates a core level electron and causes the cascade that produces the fluorescent photons whose energy determines the element it came from. I really like this slide because it demonstrates the interrelationship among many of the analytical techniques at our disposal. Whether bombarding a sample with electrons, X-rays, or ions, we're inducing a response in the material and just need to have the appropriate detection system to measure and interpret that response. Let's look at this fluorescence process in a little more detail. This simple diagram shows the first order relationship of X-ray energy to escape depth, ignoring absorption and enhancement effects that I'll touch on in a later slide. Our source X-rays penetrate tens of microns up to several millimeters into the solid, depending on the matrix. And this entire volume is the interaction zone for the processes described in the previous slide. However, the escape depths of the X-ray photons will not be the same and are strongly dependent on the energy of the specific photon. Generally speaking, escape depth decreases with photon energy, and the difference can span orders of magnitude. Let's consider a couple of examples, comparing 3 X-ray lines, aluminum, iron, and molybdenum, that span a wide energy range. Aluminum is the low energy photon here at just under 1.5 keV, while molybdenum is the highest at 17.4. And we'll also look at their behavior in a heavy element, steel, versus a light element matrix, SiO2. We see that indeed the higher energy X-rays can travel further in a solid, yielding an increased depth of analysis. But we also see that the matrix itself has a significant effect. Notice that the escape depths are significantly higher in SiO2, nearly 40 times for molybdenum, for instance. This is probably a good time to point out the role this effect plays in detection sensitivities. From these examples, we can see how the sensitivities for these elements would be much higher in SiO2 versus steel, simply because we're collecting our signal from a much larger bucket. But moving on to the lower table, we find that life isn't really just that simple. We also have secondary effects, absorption and enhancement, to consider. In this example, we again have our series of 3 elements with increasing photon energy, and we look at their behavior in aluminum metal. While we see the expected trend for sodium and magnesium, it abruptly changes direction with silicon, the most energetic of these 3 lines. So what's that all about? Well, it turns out that the silicon photon has an energy just above the aluminum absorption edge. Therefore, a significant amount of the silicon photons that are generated are reabsorbed and do not escape the matrix. The aluminum signal is enhanced in this process through secondary excitation. So not only are we sampling silicon and aluminum from only the near surface, but our sensitivity for silicon in aluminum is also somewhat compromised. A good take-home point from all of this is that for accurate quantification using XRF, the sample must be homogeneous throughout the analysis volume, from the very near surface to the maximum depth. This slide provides us with an overview of the XRF technique, but it's worth commenting on these points in more detail. While XRF is considered a non-destructive analysis technique, X-rays in and X-rays out, it's only non-destructive if the material being analyzed doesn't degrade or decompose under high-power X-rays. In fact, some materials aren't that robust. Many polymers will degrade at the high powers that WD-XRF instruments typically use. Glass presents another unique phenomenon. It doesn't degrade, but it will change color, often dramatically. We've already discussed information depth in detail and touched on detection limits. Referencing our previous slide, we can make some general conclusions. Heavy element analysis and a light element matrix will have the best sensitivity, while light elements in a heavy element matrix will have the worst. The typical ranges shown here are only for non-specific survey and meant as a guideline only. Considering the detection limits, in reality, sub-ppm detection limits are easily achieved for transition metals and other elements with high energy photons and a polymer, because our sampling depth for these elements can be several millimeters. But then consider a light element in gold or tungsten, 2 of the most dense metals. In this case, our sampling depths are probably in nanometers, leading to very poor sensitivity. XRF can measure XRF can measure areas as small as 20 microns and up to 30 millimeters in diameter based on the type of instrument, something we'll look at in more detail in the next slide. XRF also does not require a vacuum except for the lightest elements, which makes it suitable to analyze liquids directly. XRF instruments come in 2 varieties based on the system for detecting the X-rays. Energy dispersive XRF instruments, or EDXRF for short, use a solid state detector which provides fast, simultaneous detection of the elements. EDXRF instruments, in fact, use the same type of detectors as SEM-EDS instruments, and that makes sense because both techniques are measuring the same fluorescent X-rays. The difference is that EDXRF produces the signals using high-energy X-ray bombardment, while EDS uses electrons. This is a meaningful difference. The sampling volume for EDXRF is for practical purposes constant, while also much greater than EDS, which is also dependent upon the electron beam energy. For this reason, even though EDS is often used to measure compositions, the quantification is considerably more robust with EDXRF, and the sensitivities are much higher. EDXRF instruments have high signal throughput, which makes it possible to operate at very small spot sizes, down to 20 microns or so, and still perform analyses fairly quickly. Wavelength dispersive XRF, or WDXRF, utilizes diffraction of X-rays through crystals to disperse the fluorescent X-rays for detection. Crystals have known despacing, and considering Bragg's law, the photon energies can be measured based on the diffraction angles. WDXRF has significantly better energy resolution and lower backgrounds than EDXRF, and can measure all elements down to boron, or in specific applications, beryllium. WDXRF has the best accuracy and precision. However, a full elemental survey takes significantly longer than it does with EDXRF. In our Sunnyvale lab, we use only WDXRF instruments. However, in our lab in the Netherlands, we also have an EDXRF along with WDXRF for small spot analysis. This example of spectra from 3 rare earth oxides is a good comparison of energy dispersive and wavelength dispersive XRF. The rare earth elements are a good example because they have several X-ray lines and interferences are likely. Only WDXRF could unambiguously identify trace elements of one of these in a mixture like this. Note that EDXRF results are plotted as energy, just like EDS, but the WDXRF data are plotted as diffraction angle. Another good example of this would be at low levels of aluminum and silicon, or vice versa. These are very difficult with EDXRF due to strong overlap between the two signals based on their similar energies. So let's talk about quantification using XRF. With an all-purpose analytical services lab, such as EAG, we never know what might be coming in the door. As I said earlier, XRF is often utilized as a kitchen sink technique, analyzing everything but the kitchen sink or the kitchen sink as well. One of the strengths is the ability to perform robust compositional analysis without the need of standards. The so-called standardless quantification uses fundamental parameters, algorithms that use X-ray physics coupled with pure element sensitivity factors to calculate concentrations based on the relative intensities of the detected elements. Fundamental parameters, or FP, quantification, though often considered as semi-quantitative, is often more than sufficient for general compositional analysis. However, for many QC applications, the highest degree of accuracy is critical. In this case, we can produce calibrations curved from matrix max standards to maximize the accuracy. I also want to say something here about precision, which is a separate thing from accuracy. WDXRF has unrivaled inherent precision among analytical tools. For this reason, even without standards, the technique is ideal for comparing nominally identical samples to look for small differences that may be causing a property change. Now we're going to look at some real-life examples that demonstrate the versatility of XRF for materials characterization. We'll start with some basic compositional analysis of different materials, including glass, metals, and polymers, including both standardless, semi-quantitative analysis and results calibrated against reference standards. Then we'll look at a couple of more specialized applications before turning to thin film analysis. The first data set is an example of fundamental parameters quantification of 2 NIST standard reference material samples that we have available in our lab, a glass and a stainless steel. Well, as I said before, this type of compositional analysis is often referred to as semi-quantitative. We can see from the results here that if samples are properly prepared for the analysis, the results can be quite accurate. Let's now apply FP quantification to identify a couple of unknown alloys. In this case, the samples are large and we would prefer not to destroy them, so we use our large spot instrument with a sample holder designed to accommodate samples of various sizes and shapes. The results indicate that one of the flanges is 304 stainless steel, while the second is 2014 aluminum. The specifications for these 2 alloys is shown for comparison to the measured results. A comment on the 304 designation though. 304 and 302 stainless steels can't actually be distinguished by the major elements. It requires measuring carbon, which we would do with IGA if that level of certainty was required for this particular analysis. 304 is the more common alloy though, so that's likely what we're looking at here. We routinely identify or verify compositions of many types of alloys, including unambiguously distinguishing between most 300 series stainless steels, except as noted above. Since we aren't a lab supporting a small number of specific materials, it isn't possible to have standards for all of the possible materials we're asked to analyze. We therefore often rely on the fundamental parameters method. However, I'll point out that we do have many alloy and glass standards available, and when the need arises, we've also purchased additional reference materials to support specific projects. Now for a QC example, where the accuracy requirements are more stringent. The sample is an iron-nickel controlled expansion alloy. These alloys are used in applications where a specific thermal expansion is required over a given temperature range. The nickel content is a critical measurement as it determines the specific properties of the alloy. In this example, we produced a calibration curve from several nickel iron certified reference materials, and we achieved a 0.1% relative accuracy for nickel with excellent precision. Even the trace elements have good accuracy and precision using this method. 5% relative accuracy for chromium at approximately 350 ppm, for example. When the absolute highest accuracy and precision is required, WDXRF with matrix match standards is the tool of choice. Now we'll look at some other examples, polymer examples. Polymers can be analyzed by simply cutting to size, or we can even take pellets of raw material and fill sample cups. Because of how far X-rays can travel in polymers, we must make sure that we can satisfy the full analytical depth for a bulk analysis. For polymer thin films, this may mean stacking several layers to make a thick sample. The first example is an acrylonitrile butadiene styrene polymer, generally known as ABS, with a high loading of brominated flame retardants. FTIR analysis on these samples had previously identified the specific flame retardant, tetrabromobisphenol A, and XRF determined the concentration, while also finding antimony trioxide, which is often combined with brominated flame retardants. I would like to point out, though, that we don't find antimony trioxide here, only the antimony. We aren't doing chemical state analysis. But in the case of what we know about flame retardants, when we see a high antimony signal in this case, it most likely is the antimony trioxide. Our second example is a PVC material that also may have elements associated with flame retardants, specifically the antimony again, and maybe the phosphorus. But this sample has a great deal of additional filler material as well, including titanium dioxide and very likely a phthalate plasticizer based on the high oxygen content, as well as other stabilizers. While XRF would never be my first choice for polymer for identification, getting a full elemental survey in this case clearly identifies this particular polymer as polyvinyl chloride, PVC. WDXRF is a powerful tool for complete characterization of polymers because it can detect all elements from boron to uranium and has a very wide dynamic range. Thinking back to the fact that greater sampling depth yields better sensitivity, polymers represent the perfect case for achieving sub-ppm detection limits for many elements while simultaneously being able to measure the matrix level species. Now we're going to look at a specialized sample preparation tool and see what advantages it can provide for XRF analysis. Some types of samples are very heterogeneous in composition, even within a very small sampling volume. As we've seen, this scenario can create a problem for accurate XRF quantification. A method of sample preparation often utilized with XRF to overcome this issue is fusing the material into glass discs. The borate fusion process involves mixing a small amount of analyte material with a flux, most commonly a mixture of lithium metaborate and tetraborate. The ratio of the two can be varied to best dissolve the specific analyte material. The mixture is placed in a platinum crucible and heated to over 1,000 degrees centigrade while swirling to mix and dissolve. The melted material is then poured into a platinum mold and cooled to form the glass disc. The finished sample is ideal for XRF, with all components of the analyte compound distributed homogeneously as simple oxides in an amorphous single-phase glass disc. This slide shows a picture of the particular fusion oven in our lab in Sunnyvale. As mentioned in the previous slide, fusion allows us to create a homogeneous glass bead for analysis. Generally, comparing fusion beads to direct analysis of powders, both precision and accuracy can be improved by eliminating issues such as mineralogical effects and surface roughness, for example. This sample prep technique is routinely used in the cement industry, for geological materials, ores, and many other sample types. Another benefit we get from fusion is the ability to create our own standards from pure materials for specific applications. As this picture shows, we start with our flux and accurately weighed portions of our analytes, our pure element analytes, or pure material analytes, and fuse them into a glass disc that is an ideal sampling medium for XRF. In this particular case, we are creating a holmium-doped yttrium aluminum garnet standard. We simply vary the amounts of the material you want to analyze to create a set of calibration standards. These two examples show the linearity achieved by creating a set of fusion bead standards, like I just shown in the last slide, for two different applications. The first set was created for the purpose of measuring trace elements of a dopant material in YAG again. The dopants, in this case cerium, can make this material useful as a laser medium or phosphor. The second example demonstrates the creation of standards to measure zirconia content in zirconium toughened alumina, or ZTA. ZTA ceramics are known for high strength and high wear and corrosion resistance, and zirconia in particular is difficult to analyze with ICP techniques because it resists going into solution. So XRF is generally the technique of choice for measuring these types of ceramics. To summarize, we can create standards using fusion to analyze trace elements in a matrix or to accurately measure the matrix itself. All we need are the pure compounds as starting materials. For this next example, we'll look at an application for trace analysis, specifically trace hazardous metals in water. The Resource Recovery and Conservation Act, or RCRA, monitors 8 heavy metals that are considered toxic at even trace levels. The list includes arsenic, barium, cadmium, chromium, lead, mercury, selenium, and silver. While we can analyze liquids directly using WDXRF, for this example, we deposited 200 microliter aliquots of a standard RCRA metal solution at different concentrations onto specialized filter media. The solutions were allowed to dry, then analyzed. The spectrum shown is a partial one showing the mercury, lead, arsenic, and selenium signals. The peak intensities versus concentrations are shown here for these 4 metals, and again we see a nice linear response for measuring these metals over a range of concentrations in water samples. Note that this is possible even with a partial overlaps in some of the spectra. This method of analysis is very useful for applications where there is only a small volume of liquid available. Like I said, in this example, we used only 200 microliter aliquots of water to complete the tests. While this example shows water samples evaporated to dryness, I do want to stress again that XRF cannot analyze liquids directly, typically under helium atmosphere. And in fact, WDXRF is routinely used to measure wear metals in oil. We'll wrap up our set of applications now by looking at some examples of thin film analysis, including non-destructive analysis of multi-layer films, determining thickness and composition in the same measurement, and finally applying these methods to the analysis of full wafers. I have a slightly modified diagram I showed near the beginning of this presentation to reflect the process when the sample has films on the surface. Because of the large penetration and escape depth for X-rays, we can often obtain signals from multiple film layers and the substrate within the same measurement. If we know the order of the layers and which elements are associated with each, we can measure film thicknesses and compositions without the need to cross-section, sputter etch, or otherwise destroy the samples. The first example is a plating thickness measurement for gold on palladium on nickel films on a copper substrate. This system is used in semiconductor package applications. We see in the scans that we have strong signals from all 3 layers as well as the copper substrates, so we can be assured that we're capturing the full analytical volume. Since we know the order of the layers, we can use this information and the relative intensities to directly calculate the layer thicknesses. And I will stress that it is necessary to know the order of the layers. The reason is because we're simply detecting the intensities of the various elements, and buried layers will have their intensities attenuated by the layers above them. All of this information has to be captured correctly for the thin film model to accurately process the data. We first allow the software to calculate thicknesses using FP approach, and the results correlate to the true thicknesses very well. We do begin to see greater error in the bottom nickel layer though, and this is reasonable because the nickel signal is being attenuated by both the palladium and the gold layers, and any small error in the calculated thicknesses of those upper layers will carry through to the nickel thickness calculation. But as is always the case, if we have appropriate standards, we can create a calibration curve and we can improve the accuracy of the measurement for all three layers. In this next example, we measure the thickness and composition of an indium tin oxide film on glass. The spectrum shows the indium and tin K-alpha peaks that we use for the analysis, and we allow the fundamental parameters method to determine both the thickness and composition for this thin film. With an instrument that can accommodate large samples, we can employ WD-XRF to the analysis of thin films on full wafers. In this first example, we're measuring the scandium concentration in aluminum scandium nitride thin films on 6-inch wafers. For this analysis, we obtained thickness and scandium concentrations from the centers of 4 wafers using Rutherford backscattering, RBS, and created a calibration curve to measure the rest of the points on the wafers. RBS is a first principles analysis technique that is used to measure thickness and composition of thin films. It's a powerful technique in its own right, and I hope you'll all tune in for this seminar on May 13th. What's being shown here are the discrete measurement locations analyzed using a 10mm diameter spot size. The legend in the upper right gives the range of scandium concentrations in atomic percent, and we're measuring approximately a 2% variation in standard concentration across the wafer. And finally, in this last example, we obtained a thickness and density measurement from the center of a 300mm half wafer using XRF, and use that data to measure several points by XRF over the wafer and generate thickness maps for both tungsten and titanium nitride. XRF can measure any thin film or film stack as long as the layers are thin enough for all signals to escape and be detected. And importantly, there aren't common elements in different layers or between substrate and films. Sometimes if those latter issues exist, they can be overcome, but very often not. We've accurately measured metal films in our lab using WD-XRF ranging from several microns in thickness down to less than 10 angstroms. And that brings us to the end, so let me summarize the high points. XRF is a technique that can accurately measure compositions of practically any solid. Standards are generally not required, but the accuracy will always be better with matrix max standards for calibration. The technique can be used for non-destructive characterization of thin films, including both thickness and composition. It doesn't require a vacuum, although vacuum significantly improves the sensitivities for measuring light elements. And since a vacuum is not required, XRF can directly analyze liquids. Since XRF is X-rays in and X-rays out, it doesn't have issues with charge buildup that electron-based techniques have. And as I noted earlier, the technique is generally considered to be non-destructive, but there are exceptions to every rule. There are materials that will degrade under high-power X-ray bombardment. With the appropriate instrumentation, we can measure large samples, as I've shown, both full wafers for thin film mapping and large samples for non-destructive compositional measurements. Regarding limitations, I've listed the spot size as one. The sensitivity of WD-XRF varies significantly with spot size. And while we can go down to 500 microns spot size with our tools, the sensitivity at this spot size for trace element analysis is limited. ED-XRF affords much better sensitivity for micro XRF. However, considering techniques such as Auger electron spectroscopy or SEM-EDS, 20 microns is still a relatively large area to analyze, particularly when you're talking about semiconductor applications where where devices on circuit boards can be very small. The last 2 points are related. When analyzing solids, we have to remember that XRF is essentially a surface analysis technique, albeit with several microns to millimeter sampling depth. Therefore, sample homogeneity between near surface and bulk is critical for accurate compositional measurements. As I mentioned early on, EAG has a wide variety of diverse techniques at our fingertips, and often literally just down the hall. The SMART chart can serve as a guide to compare and contrast analytical techniques to determine which one is applicable to the problem at hand. But it's also worth pointing out that since no analytical technique can serve as an all-purpose black box of answers, we find many situations where multiple techniques are necessary to get the full picture. I'd mentioned SEM-EDS as a technique that provides similar information as XRF, indeed in measuring the same fluorescence signal. While EDS is less robust for quantification, it has the advantage of being more surface sensitive as well as having a significantly smaller spot size. Total reflection XRF, or TXRF, is a specialized type of XRF where the incident X-ray beam hits the sample at a grazing angle. TXRF is a very powerful technique for measuring trace levels of surface metals on atomically smooth surfaces, such as semiconductor wafers. While the physical processes are essentially the same, TXRF is a completely different technique with its own unique instrumentation. We'll consider the SMART chart webinar series over the next several weeks to explore more of these techniques. So why choose EAG? There are several reasons, but I think it's important to state right at the top that client confidentiality is core to our business. We're a global leader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. Finally, I'd like to make a couple of points in light of the pandemic that's affecting us all right now. I want to stress that EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we've complied with the latest COVID-19 regulations from state and local governments, as well as the Centers for Disease Control. Currently, all of our locations throughout the world remain open, but we may have limitations on customer visits. As this is a fluid situation where we are definitely operating a laboratory at reduced capacity, we can also transfer samples to another EAG location as need be. We encourage you to discuss your options with our sales representative.